Terima kasih yang berbahagia Tuan Pengerusi. Selamat petang tuan-tuan dan puan-puan. Izinkan saya membuat persembahan ini dalam bahasa Inggeris. On the early warning systems of natural disasters, I shall do a very what I call simple presentation on the natural hazards affecting Malaysia, then the early warning systems for risk management, and talk about the multi-hazard warning system that is at the Malaysian Meteorological Department. We are only doing two of the early warning system on weather and climate and earthquakes and tsunamis. There are also other natural disaster early warning systems that are with the other departments. For example, the landslides is with the JKR. And have some concluding remarks. I would not be doing the applications of GIS in the earlier part of the presentation, but towards the end, I will then inform how important GIS will be in the future early warning systems. On the natural hazards affecting Malaysia, you'll see that we have actually, where most of you are most familiar is with the monsoon floods in the East Coast. But more recently, you will be seeing more and more of the flash floods, as you have seen in Kuala Lumpur, in this Ulu Langat area in Klang, in view of the development that's going on and the interaction of what they call the weather extremes with the development. Also, the thunderstorms and associated lightnings, we are actually seeing more severe thunderstorms. Some of people say this is due to climate change. There is some truth in this. Not only in our country, but also in our neighboring country. I've been recently being informed by the Indonesia, the deputy, that they are also seeing more tornadoes, the small mini tornadoes in Indonesia itself, which in Malaysia, afterwards I'll be showing you that we are also seeing more of this. On tropical cyclones and typhoons, we rarely get them, but that is the problem. Once it occurs, we don't have enough experience. In fact, the local population itself don't have enough experience to be able to withstand these type of natural disasters. The other one is the forest fires and haze, which we are now into the southwest monsoon season. It's getting drier. This year, probably we will be seeing haze again. And of course, the other one is agricultural droughts. This does occur, but it's not really that frequent in Malaysia. The other one is earthquakes and tsunamis. We have seen the recent 11th April, the two big earthquakes that occurred, although it did not cause a tsunami. I'll brief a little bit on that, the risk that we are facing. And landslides, volcanic eruptions is not in our country, but our neighboring countries. You have seen that the volcanic eruptions actually has an implication to us, especially on the civil aviation flights. These are some examples of the severe weather. The floods is in the northeast monsoon, mostly in the east coast. The inter-monsoon, we'll get the flash floods. Southwest monsoon, then comes haze, and then of course in the during the northeast monsoon, you have the strong winds and the rough seas in the east coast, and some of them are actually leading to very severe erosion along the coastal areas in Kelantan and Terengganu. From 2005 to 2009, these are some of the examples of the severe weather we are seeing. And in fact, over the last 7 or 8 years or so, we are seeing more and more weather extremes occurring in Malaysia. I do believe that this is part and parcel of the changing climate that is going on. And this is an example in Sarawak. In the thunderstorms, we are seeing more and more severe thunderstorms, and we are also seeing more and more of the water spout, and also the mini tornadoes on land. There's one at Bukit Kriang, Kedah on March 2011 over the paddy fields. In the Pulau Pinang part in 2010, and Jajawa in Perlis, October 2010 also. This, I think, the neighboring countries are also seeing more and more of this. And I do believe that this is part and parcel of the changing climate we are seeing. But the good thing is that this water spout and tornadoes that we are seeing, in the tropics, it cannot get very severe. You will not see those that you see in US or in the, what you call in the other countries like China and so forth. The reason being the thunderstorms cannot form such intense tornadoes. So we'll get small, intense tornadoes, enough to damage 10 to about sometimes 100 houses, but most of them are the roofs blown off, the trees blown down, and so forth. Southwest monsoon, usually the severe weather we are seeing is mostly due to El Nino. The worst one was in 1997. We are actually more than 15 years due for another strong El Nino. In 1997, when it occurred, you find on the bottom right hand, you see the white color. Those are the haze from the what we call the burning that is occurring in our neighboring country. In our neighboring country, it has very what we call thick peatland, and when it gets very dry, sometimes it can ignite by itself. The burning of the peat goes very deep in, and there is no way to control. So this is one of in the Southwest monsoon. This is one of the extremes that we are facing. The other one on the earthquakes. This is until 2004. You'll find that You'll find that we are sitting on the ring of fire. Now, from the Aceh in December 2004, the big earthquake that occurs here, there was a tsunami. The risk zone is along here, has been predicted along here, near the Palembang area. Near the Bengkulu area, and also the Mentawai Islands around this side. Now, the Mentawai Island, according to the scientists, there is still a very big pressure being built up there, and they are still thinking a very big earthquake would occur below the Mentawai Islands. On April 11th, we had two earthquakes that occur off Aceh. It was further westward of Aceh, and luckily it was not what we call a vertical displacement, but it was a strike slip where it was actually a horizontal movement with a magnitude of around between 8.7 to 8.9 and the second one was 8.5. Usually strike slips does not have such big magnitudes. So it was the first time you get a strike slip more than 8.0. So it's actually a new, what they call new understanding going on in this place. But the worry for this is this thing. If you look at this part, whether another set of pressure is building up along the area or not, this is still under study. We have asked the what they call Oceanographic Commission, Intergovernmental Oceanographic Commission under UNESCO to study whether the pressure is again building up along here. And if it is, then there is a risk there of another big earthquake that can cause a tsunami over that region. Out from the Japan's earthquake, this part is also under risk. There is what they call a Manila Trench over the other side, which we think that it's overdue for more than 100 years for another big earthquake to occur over the site, which will then affect these countries over here and also our region. Okay, usually for the tsunamis, if it occurs over the Andaman Sea, we have about 2 hours. But if a big one occurs near the Nicobar Islands, we actually have less than two hours to react. Hence, the reaction of the people knowing how to move in these early warning systems is very important. I shall skip this. This part, the mitigation and preparedness needs to be done, and that is where the application of GIS part is very important, because this is the part that can show us where the risk zones are, and to use it for the planning and for the mitigation part. The prediction and warning part uses less of the GIS, but for the disaster management and also the impact in the recovery part, the impact and response, and the crisis management, the recovery and reconstruction, actually GIS is a very, very useful tool for such managements, especially when it's what they call used in conjunction with the satellite images. And for the early warning system, there are 4 areas that we need to do. One is the risk knowledge study. The other one is the monitoring and the warning service itself. And also then the dissemination and the communication of the warning. The last part is the response capability of the local authorities and the people. I shall skip this. So I shall look at the weather monitoring and prediction system, which is coupled with also a sea state monitoring and prediction system, and the earthquake monitoring and tsunami early warning system. As you see, this covers 4 parts: risk knowledge, which GIS applications in this would be very useful, and then the monitoring and the warning system service. Usually in a warning, you will tend to overwarn because by virtue that what you call there is a certain amount of error in the prediction. Hence, the application of GIS for precise application in a warning system is not that useful. But as the prediction gets more and more accurate, I think more and more application of the GIS will be used in the warning system. Communication and dissemination, I'll talk about it later, and the response capability of the people and also the local authorities and the disaster management people itself. For example, the 999 and so forth, I think those systems will be very useful in the response capability part of the local communities. Currently, the early warning systems uses TV and radio. It also has SMS broadcasting. We tried to implement cell broadcasting, but that has not taken off because of the amount of money that is involved. The printed media, the good thing is that most of the newspapers have their own online publication now. And during what I call warning systems, they tend to update very fast. And that gives us what I call an advantage on the online this. We also have a fixed line disaster alert system through using telephones. That means if there is a need, for example, for evacuation during tsunamis, the phone in those districts that are involved 5 kilometers from the shore will ring. And there will be a message. This is done with Telecom Malaysia. And of course, there are sirens, but sirens, we have only 23 sirens. Is not enough. Indonesia currently has only 31 sirens, which is also not enough. This is what the prediction system is all about. The observations comes in. It has a computer system to do the processing and also the prediction forward, and then issue the forecast. It does not use very much GIS yet by virtue that the prediction part is not accurate to what you call about 100 meters or so forth. So it's very difficult to use GIS to convey the message out to the local authority because it will give what call a false perception to the people. And the prediction system is actually very complicated, although it can be used for social decisions, economic decisions, environmental decisions, and security decisions. Probably at the decision part where the GIS application will come in for this. For example, on the environmental decision, we are now developing what we call the fire danger rating system using Google mapping, overlaying the information. And the other part is that on the forecast part, the accuracy part, you'll find that because of the nature of the prediction system itself, the accuracy tapers off very fast. Within 7 days, actually, there is no predictability left. But on the seasonal time scale, there is some predictability. The reason is that a lot of the weather systems are anchored by the sea surface temperature, how warm the oceans are, and also by what we call the topographic landscape. And so it has a very unique way that you can have prediction accuracy, can have some accuracy within the first 7 days, and you can talk about a season, but in between, it's very difficult to predict the the prediction part. I think that the GIS will become more and more useful if the prediction systems gets more and more refined in the what you call the resolution of the prediction. Currently at the Malaysian Meteorological Department, we are running the system at 4 kilometers only. We think that a future system of less than 1 kilometer resolution would give the type of accuracy that you see by virtue that a lot of it is anchored by the topography itself. But such a system will cost at least 70-80 million Malaysian ringgit, which currently still is difficult to get funding from EPU to move into that direction. On the longer range forecast, the long-term projections, as you see in the climate change that people talk about, those are even more cost in the predictions. But although people does downscaling and then apply it as if it's very accurate, actually it's giving some perception on what the impact is, but the real accuracies are not there yet to do those at this type of scale. And at the World Meteorological Organization, what it's doing is that it's trying to move into a global framework for climate services, where it's trying to meet the unmet needs, where there should be, from the prediction system, there needs to be a user interface program to go into the different applications. And I think it is from here that then the GIS applications will start to move. So my feeling is that the GIS will have a greater and greater impact on the forecasting systems, in the applications for the forecasting systems in the future. On the multi-hazard early warning systems on the earthquakes and tsunamis, currently in Malaysia there are 17 seismic stations, and this then complements the what you call the seismic stations that are in the region. So when an earthquake occurs, when the seismic waves reaches our region, then we will then know, as we compute backwards, we will know where the earthquake occurs and what is the strength. Usually for those occurring in Sumatra, within 4 minutes, we will know where the earthquake is. And within the 10 minutes, then the information will go out. So the tsunami early warning system is on a 10-minute timeline. In Indonesia, they do it differently because the earthquake is at the shore of the what they call the zone. And what happens is that if an earthquake occurs, and if they straight away they know the magnitude, they will straight away, the local authorities will straight away sound a siren. So the tsunami early warning system at the local level is on a 5-minute time frame. And once a siren is sounded, the people will then just evacuate by themselves. We have also done a tsunami modeling database because once an earthquake occurs, you have only less than 2 hours. You cannot go and predict. You cannot go and compute at that time. So what we do is we know where the risk zones are, and we compute it for different scenarios and then store it as a database. And from there, we will be able to tell that if an earthquake occurs at that place with this magnitude, what is the arrival time to Malaysia at each of the locations, and what is the tsunami height. For the April 11th one, the computed one, if it occurs and arrives in Langkawi, was roughly about 0.8 meters if it has occurred as a vertical, what they call earthquake. What do you call that? The movement has been vertical, but fortunately it was the horizontal motion. And there are also tide gauges along Malaysia and also internationally to measure the tsunamis once they arrive at the local place. And this is on what you call the communications with the neighbors in this monitoring system. Everything, once an earthquake occurs and the tsunami forecast is issued, everything occurs within the 1 hour. And that is the type of time frame that we need to react, including the people that is doing disaster management on the ground. It's actually a very big challenge, especially if it occurs at night. How do we then, if it really occurs, how do we warn the people to evacuate within that 1 hour? There are coastal cameras. Coastal cameras are only useful during the daytime. Currently, they are on 18 sites. For example, on the April 11th, the earthquake and the tsunami warning that was issued, we had one coastal camera in Kuala Muda. We were seeing from the coastal cameras that there was people, including a lady carrying a baby, standing and watching whether a tsunami is coming in or not. So those are the type of usefulness on the coastal camera, but the problem is it's very limited. It's very limited. It can only be used during the daytime for us to be able to help in the evacuate, what they call the evacuation, and also keeping the people away from the risk areas during a warning. So my concluding remarks is that we need higher accuracy weather and climate forecasts at the local level, and a shorter timeline with accuracy of tsunami warning after earthquake occurs. Once this type of accuracy becomes more and more accurate, I think GIS applications into early warning systems will be very useful. Currently, I think the most useful part of the GIS will be during what we call the recovery and the mitigation part applications. Awareness programs for both tsunami and weather extremes are very important. I shall share with you a story that occurred in Aceh. Was told to us. We had a brainstorming 3 weeks ago among the Southeast Asian countries on the April 11 earthquake, and this was what was told to us by the deputy head of the Bureau of Meteorology and Geophysics in Indonesia. When they carried out the tsunami drills in Aceh, everything was working fine. They had quite a number of drills. But when April 11th, the warning went out, everybody took their cars to evacuate. So all the roads were jammed up. They couldn't do the evacuation. So those are really lessons learned during evacuation. In fact, we had a drill following that in Batu Ferringhi in Penang. And the what I call the police and also the local management, disaster management people were also telling us that during the time when it was occurring, everybody was trying to go back from Batu Ferringhi back to Georgetown with this. So if a tsunami has occurs, then it will be very difficult to do evacuation. So those are the type of lessons we learned along the way. Also, there is a need for what we call in fact, the application of GIS was very important on the evacuation routes in each of the districts and in each of the Kawasan part that we need to really identify so that the people are prepared and know what to do. And also there needs to be better coordination between disaster management agencies, and also needs better risk assessments part. This is a continuation process which needs to be done, carried out, not only by the disaster management agencies, but also by the local authorities. Thank you.